Okay, so last time we talked about atmospheric stability and how that influences the kinds of clouds that form or don't form on any given day. And we spent most of our time talking about conditionally unstable environments and cumulus clouds, which are the kinds of clouds that form in conditionally unstable environments. So that's going to lead naturally here into a discussion of a particular kind of cumulus cloud, which is the thunderstorm. The thunderstorm. So let's start off here with a quick definition. So maybe as a working definition of a thunderstorm, we can say that a thunderstorm is a cumulonimbus cloud or a collection of cumulonimbus clouds. So cumulonimbus cloud or a collection of cumulonimbus clouds that typically feature vigorous updrafts in the cloud, along with significant precipitation and lightning. Vigorous updrafts, precipitation, and lightning. Now, it's really the lightning here that's the defining feature of the thunderstorm, because if you have lightning, you also have thunder, and that's a storm that produces thunder will be a thunderstorm. But thunderstorms typically also produce significant precipitation. There are certain kinds of thunderstorms that don't produce a whole lot of precipitation at the ground, but even in those cases, you'll have precipitation up in the cloud. Now, I should just point out that if you'll remember by definition, a cumulonimbus cloud is really just any cumulus cloud that produces precipitation. But in the context of thunderstorms, we're really thinking of sort of the deep cumulonimbus clouds, the clouds that extend through a significant portion of the troposphere. So in the figure down here, or the photo down here, we've got several examples. So this is showing a series of thunderstorms over the Amazon basin. And each one of these guys is a vigorous updraft, a cumulonimbus cloud with a vigorous updraft that extends through a significant portion of the troposphere. In fact, it probably extends all the way up to the top of the troposphere. When it hits the stratosphere, it tends to flatten out because the stratosphere is a very stable environment, and so it can't rise anymore. So the updraft reaches the stratosphere, and then it sort of flattens out. So you can sort of see the flat tops on each one of these storms, but then in the middle, you've got an updraft that's still sort of bubbling up here in the center. Now, thunderstorms are important, as you expect, because they produce a lot of what we consider to be severe weather, including things like high winds, lightning, tornadoes, hail, stuff like that. Now, by definition, if we're thinking about severe thunderstorms, if you have a severe thunderstorm warning or a severe thunderstorm watch from the Weather Service, what do they mean by that? Well, by definition, a severe thunderstorm is a storm that's going to produce one of the following, at least one of the following. Large hail of 3/4 inch diameter or greater. Actually, I forgot to change this. This is the old rule. Not that it really matters, the details here. But the old rule was 3/4 inch hail. The new rule, I think as of a couple years ago, is 1 inch hail. So this has actually been updated a little bit. But regardless, produces large hail. Strong wind gusts of at least 50 knots. So a little more than 50, well, I guess 55, 57 miles per hour. Or a tornado. So a severe thunderstorm is a storm that produces one of those three things. Now, again, a thunderstorm is really just a type of cumulus cloud. So all the kinds of things that we talked about when discussing cumulus clouds apply to thunderstorms as well. And sort of the most important thing here is that a cumulus cloud continues to rise because it's warm. And the reason it's warm is because you have condensation in the cloud, which is keeping the updraft warm. So what that means is that the fuel for your thunderstorm, the thing that drives it, is really going to be condensation in your cloud. So if the fuel for the thunderstorm is condensation in the cloud, because that's what keeps the cloudy air warmer than the surrounding environment and thus continues to drive it upwards. So this is going to be important then, because in order to have a significant thunderstorm, you're going to have conditions that allow you to produce significant condensation in your cloud in order to keep driving the plume upwards. Okay, let's go through and talk a little bit about the anatomy of a thunderstorm. And thunderstorms, in most cases, are built up of a type of building block, which we refer to as a thunderstorm cell. So a thunderstorm cell is kind of the building block of a bigger thunderstorm. So let's go through and talk about a thunderstorm cell in particular and label its parts. Describe sort of what its basic features are. So we're going to sketch this in. Let's start off by putting the ground in down here. And then we've got our thunderstorm up here above it. Sort of towering cumulus cloud. And so with that, now that we have our cloud in there, let's go ahead and give a definition of what we mean by a thunderstorm cell. So what is a thunderstorm cell? Well, a mature thunderstorm cell, one that's sort of developed to its full form, is a structure that consists of a warm updraft along with a relatively cold downdraft, that is a descending flow. So you have both an ascending flow in your cell as well as a descending flow. So warm updraft and relatively cold downdraft. So let's go ahead and sketch this in here in our thunderstorm cell. So here's our updraft, sort of ascending into the cloud. Put a few arrows on here so we indicate what direction it's going. And remember, the updraft is ascending because it's warm. It's warmer than the surrounding environment, and that's why it continues to ascend. It's buoyant. And the reason that it's warmer than the surrounding environment is because we have condensation in the cloud, which releases latent heat. So that's the updraft part of it. But a mature thunderstorm cell, once it's sort of developed into its mature structure, also has a downdraft associated with it. So let's sketch in the downdraft here. So we've got our descending flow coming out of the cloud. And what's driving this? What's driving the downdraft? Well, it's actually a couple things. Part of it has to do with the fact that there's precipitation, rain and hail and things like that, falling, and that exerts some drag on the air. And so it actually has an effect of pulling the air down. So precipitation, if you have a significant precipitation core falling out of the cloud, that'll tend to pull some air down with it. That's part of it. The other part of it is that as the rain falls into the air below the cloud, it starts to evaporate. And you'll remember that evaporation is a cooling process. So the rain falling into the air below cloud evaporates, that cools the air, and so you end up getting heavy, dense air, and that also tends to drive it downwards, because if it's dense, it wants to fall. So it's those two things. It's the drag associated with the falling rain, and also the fact that it's cold because it's evaporating. Now, in addition to the rain evaporating below the cloud, you also tend to get some evaporation within the cloud. And typically the way that works is at the edges, because at the edges, things tend to be pretty turbulent. It's pretty turbulent throughout the cloud. But that turbulence at the edges will take some of the cloudy air and sort of feed it out into the unsaturated environment, and it'll take some of the dry air and pull it into the cloud. And so you end up mixing some of the dry air with the cloudy air, which is going to lead to evaporation. This process of mixing together the cloudy and dry air at the sides of the cloud, that's got a name. It's called entrainment. Entrainment. You're entraining dry air into the cloud. It's actually one of the limiting factors in terms of, how fast and how far the cloud can grow, because this is sort of a drag on its growth. Every time you pull in some dry air into the cloud, and part of the cloudy air evaporates, then it gets a little bit colder, which tends to put a damping effect on the updraft. Okay, so what else? Well, as I mentioned, this air that's falling downward out of the cloud tends to be cold because of evaporation. So you end up, after a little while of that, you end up getting this sort of a dome of cold air building up at the ground. So we could sort of draw in the edges then of some region of cold air. We've got cold air descending out of the cloud, but then it sort of builds up at the ground. And because it's heavy and dense, it starts to spread. So this sort of reservoir of cold air below the cloud, this guy has a name. It's called the cold pool. The cold pool. Sort of dome of cold air that builds up below the cloud through evaporation. And again, because it's heavy and dense, it wants to spread. And the leading edge of this spreading cold air is kind of important, so we have a name for that as well. That's called the gust front. The leading edge of this guy is called the gust front. We'll come back to the gust front here in a second. So this is the basic structure of the thunderstorm cell. I probably should have pointed out too along the way that a lot of this stuff I just said is actually written on the next slide here. So I've sort of written out the notes there, but I wanted to say it as I was pointing at the structure of the storm here. So this is the basic structure of a thunderstorm cell, your warm updraft, your cold downdraft. You've got entrainment across the sides, and then you've got your spreading cold pool with the associated gust front at the leading edge of the cold pool. Now, I'll point out that as we'll see here in a few minutes, a given thunderstorm can actually have a number of these cells evolving together, but this is sort of the building block. Now, it's worth saying a few more words about the gust front, because the gust front in particular tends to be kind of important. And the reason is that the air within that cold pool, by definition, is cold, and so as it spreads, it's heavy and dense, and so it wants to dig underneath the warm air in the environment. So we've got our gust front here as the leading edge of the cold pool, and the cold pool itself is cold, whereas the air in the environment is warm. And so the cold air wants to dig its way under. This is just like the sea breeze front we talked about early in the course, where the cold air is wanting to dig its way under the warm air, and it ends up kicking the warm air upwards here. And the reason this is important is because under the right conditions, when you kick the warm air upwards like this, you can actually kick off another updraft. And so you can produce a whole new thunderstorm cell that way. So it's kind of a self-regenerating process. As the gust front spreads along, it kicks off another updraft. Now, as we'll see in a second, that's not what always happens. Under certain environments, this instead tends to kill the updraft off. But if the conditions are right, it'll serve to actually produce a new updraft instead of killing off the old updraft, instead of just killing off the old updraft. You can actually see these gust fronts coming if you sort of know what you're looking for. Because they're pretty well defined in most cases. This is one that I saw, can't remember if this was this spring or last spring, but I had just picked up my son from daycare and we were about to go out for a walk and I saw this thing coming. I actually saw it quite a bit in the distance from, before this picture was taken, and I could see it spreading to us as we waited. And knowing what it was, we didn't go for a walk, obviously. But what happens is that the cold air, which is the air on the back side of this guy, as it spreads along the ground, once it goes past you, all of a sudden the temperature drops because all of a sudden you're in the cold pool. And so the temperature drops, and it also gets very windy. And so that's where the name comes from. As this guy goes by you, it tends to get very windy, and the temperature drops. Okay, let's talk about some of the things that we need in the environment to support thunderstorm formation. So, a few things that the environment has to have to support thunderstorms. The first is that there has to be a plentiful supply, a liberal supply of warm, humid air. Now, the key feature here is the humid part, because, the thing that drives the thunderstorm is condensation in the cloud. So you're going to have to feed a lot of humid air into the cloud to keep it going. The warm part helps out as well, because if the air down near the ground is warm, then it's more likely to stay warm as it rises through the atmosphere. That said, you can get thunderstorms in winter. They're less common, but you can get them in winter. As long as you have sufficient humidity. Now, I should also say that warm also plays a role, because warm air will hold more water vapor before it becomes saturated. So the warmer the air is, the more likely it is that you have a lot of water vapor in the air. And that's why we get so many more thunderstorms in the spring than we do in the winter, for instance. Okay, so we need warm, humid air to feed into the cloud. The second thing that we need is a conditionally unstable environment. In principle, it could also be just a strictly unstable environment, but in practice, that never really happens through the depth of the troposphere. So what we get instead is a conditionally unstable environment. And so that's what we need in order to allow the cumulus cloud to grow, because if the environment were stable, then the plume wouldn't be able to rise and you wouldn't get your thunderstorm. So in order to produce a thunderstorm, we're going to have an environment that is conditionally unstable to support its growth. And then finally, we're going to need some sort of lifting mechanism or trigger in order to lift the dry air below the cloud up to saturation. And again, the basic idea was that the air in the cloud, the rising air, doesn't become warm until it actually hits the cloud, because before the cloud base, it's dry. In a conditionally unstable environment, dry air wants to fall back down. So it's not up until it gets into the cloud and condensation starts to happen that it can continue to rise on its own. So what that means is, in order to start this off, we're going to have some lifting mechanism that lifts the dry air up into the cloud, and that's our trigger. Okay, so these are basically all the things that we needed for cumulus clouds to form. Now, if you have all of these properties in sufficient amounts, then you'll kick off thunderstorms. These are just the ingredients, that sufficient ingredients, if you like, to produce thunderstorms. But it doesn't necessarily mean that you're going to produce severe thunderstorms. Severe thunderstorms have an additional requirement, an additional ingredient required. And that additional ingredient has to do with the winds, the wind profile in the environment. So specifically, severe storms require a significant change in the background winds in terms of the speed and direction of the winds. So a change in the background wind speed and or direction with height. So as you go upwards through the atmosphere, the winds have to be getting faster and or changing direction with height. This is referred to as wind shear. It's the term we use for this. This is just a sort of little schematic example here. We're at the ground. We had the winds coming from the east, but then as you go upwards, it shifts to westerly winds and then stronger and stronger winds. So this is a change in the direction and speed of the winds with height. Should note that the change in direction could also be sort of swinging around. So it could be, easterly at the ground and swing around to southerly as you go up, and then eventually over to westerly. That's a pretty typical type of profile of the winds with height. And that change in direction, again, can help to feed into the production of severe storms. Either way, change of speed and direction is the kind of thing that we need. We need significant wind shear in order to get severe thunderstorms. So just to reinforce this point about the dependence on the shear, the wind shear in the environment, So the basic idea is that given the basic conditions that we need to produce thunderstorms, i.e. the warm, humid air, the conditionally unstable environment, and the lifting, once those conditions are satisfied, then it turns out that the kind of storm that you get is to a large extent determined by the amount of wind shear that you have in your environment. And the type of wind shear as well also plays a role. So it's strongly influenced by the wind profile of the environment, i.e. the environmental shear. Sometimes it's called the background shear, just the wind profile with height. And the general rule of thumb is that, in general, more wind shear in the environment tends to produce more severe and longer-lived systems. So tends to produce longer-lived and more intense storms, let's say. So the more wind shear you have in your environment, it's more likely that you're going to produce a long-lived and more intense storm. Now, again, let's say, there are subtleties to this. The type of shear, how the wind profile varies in detail does matter. But generally speaking, more shear tends to produce longer-lived and more intense storms. Now, sort of as an extension of that, what that means down here on the bottom is that severe thunderstorms, and in particular the kinds of storms that produce tornadoes and tornado outbreaks, they typically tend to occur, or often at least tend to occur, under a branch of the jet stream. So when you have a branch of the jet stream sort of moving over a region where all the other conditions are satisfied, that's the kind of environment in which you tend to produce really severe storms and the kind of storms that lead to tornadoes. We'll actually show some examples of that. I'll actually have an example of that on the next slide. Here it is. So this is the conditions that associated with a tornado outbreak back in 2011. 2011 was a big year for tornado outbreaks in the U.S. It set a record for number of, I can't remember exactly what the record was. Number of deaths by tornadoes, I think, was the record. It wasn't actually a record for number of tornadoes. But regardless, there were several big tornado outbreaks that occurred that year. One of them was the Tax Day outbreak on April 15th, 2011. And this is a schematic showing the setup for that day. And showing things here at a couple different levels. You've got the stuff going on at the ground with your fronts, your cold front, your warm front. You've got your low center down at the ground here. I think that's the bottom L. Maybe it's the top L. It looks like it must be the top L. Doesn't really matter. And these green arrows here are showing the flow out in front of the cold front. It's tending to pull this warm, humid air off of the Gulf. So that's all stuff going on at the ground. And then at upper levels, these white arrows are showing what's going on in terms of the jet stream. So this is sort of the basic path of the jet stream on this day. And you can see how the jet stream sort of dipped down over this region here, where you're drawing the warm, humid air off of the Gulf. So if we go through our sort of list of things that we need for thunderstorms and sort of point out where they are on this thing, the first, you need a supply of warm, humid air, and that's provided by this air coming off of the Gulf here, which obviously is going to be very humid, and on this particular day it was pretty warm as well. And so you're tending to build up a supply of warm, humid air down near the ground out in front of the cold front. Second thing we needed was conditionally unstable environment. You can't actually infer that from this chart. You actually need to know something about the temperature profile with height. But I'll just state that on this particular day, you had a fairly significantly unstable or conditionally unstable environmental profile. So that was satisfied. Third thing that we need is a lifting mechanism. There's actually two lifting mechanisms here sort of built in. The first is the cold front sweeping through here, sweeping through the Gulf states. And so what happens at the cold front again is you've got your cold air on the back side sort of digging its way under the warmer air out in front and kicking it upwards, and that tends to kick off thunderstorms. So that's one lifting mechanism, the cold front. The second lifting mechanism is more subtle, and that has to do with the fact that the jet stream was dipping down here and producing a pretty significant trough. And remember, on the front side of a trough, we tend to get divergence at upper levels. Well, so that right in this region here above the warm, humid air, we're going to tend to have divergence at upper levels. And divergence at upper levels is pulling air, away from the column at upper levels, and that tends to draw air upwards to replace it. So that's another lifting mechanism. Divergence at upper levels tends to pull air upwards to replace it. And so you tend to get some lifting associated with the trough on the front side of the trough because of that. So two mechanisms for lifting. And then finally, in order to get severe storms, we need significant wind shear. And that's what the jet is providing here. So we've got at the ground, we have fairly, relatively weak winds coming off of the Gulf. And then aloft, we've got this really strong jet stream that's sort of dipping down over that same region. And so that's going to give us a really strong change in the winds with height, which is what we need in order to produce severe storms. And this is kind of a classic setup for big tornado systems, tornado outbreaks over the U.S. It's this kind of setup where you get a cyclone propagating through, typically in spring, because in summer they tend to push too far northward. But in spring, these guys are still propagating through down here through the Gulf states. And as the cold front propagates through and you're drawing air off of the Gulf and all these things, and the jet is dipping down, all these environments, all these ingredients are coming together to produce severe storms. This is actually why, because this is such a favorable setup for severe storms, this kind of region here, this is why we tend to get more tornadoes in the U.S. than any other country. Okay, let's talk a little bit about how thunderstorms are classified into different groups. So let's talk about thunderstorm classification. The basic groupings, different classifications of thunderstorms, they're pretty straightforward. Kind of goes like this. The first category of thunderstorms is referred to as the single-cell storm, the single-cell thunderstorm. And as the name suggests, a single-cell storm is just a storm that consists of a single updraft, downdraft pair, a single thunderstorm cell. This is actually the most common kind of storm, but it's also the least interesting. It's the weakest kind of storm. Has several other names. Sometimes you hear these things referred to as air mass thunderstorms or ordinary cell thunderstorms. All of those refer to the same kind of thing, just a single thunderstorm cell that grows and dies over some time period. So stepping up to the next category will be a multi-cell storm. I bet you can guess what that's going to be. That's going to consist of several thunderstorm cells that are evolving together. So several thunderstorm cells evolving together is a multi-cell storm. And then finally, the third category of thunderstorms is going to be the supercell storm. So the supercell storm, which consists of a single intense rotating updraft. Single intense rotating updraft. And associated downdrafts. Typically there's one or two downdrafts associated with this rotating updraft. This is actually the most severe kind of storm. It's the one that produces most of the tornadoes, at least the intense tornadoes. And really the defining characteristic of this is the fact that the updraft is rotating. We'll talk a little bit about why that is, why the updraft is rotating in the next screencast. But for the moment, we'll just point out that this is the sort of defining characteristic of the supercell. And even though the supercell is only one updraft and one downdraft, so essentially by definition it's one cell, it's a very intense cell and a very long-lived cell, much more so than the single cell storm. So let's go through these one by one and just sort of define the characteristics. So first, the single cell storm. As we said, that's just a single updraft, downdraft pair. This is the kind of storm that typically tends to evolve. It happens all the time. It's the kind of storm that builds, and then you might get a little bit of rain out of it, and then it dies off. And that whole thing occurs over a time scale of maybe, 40 minutes to an hour or something like that. And as I noted here, it tends to move just following whatever the winds are in the mid-troposphere, basically. That's how it propagates, just follows the winds. And when do single-cell storms form? Well, single-cell storms tend to form in environments that have relatively weak wind shear. Single-cell storms form in environments with weak wind shear. As we noted, typically more wind shear means a more intense storm, and the single-cell storm is the least intense storm, so it tends to form in environments that have relatively little wind shear. This is what the life cycle of one of these guys tends to look like. It just goes through a series of stages. They're not really that interesting, but so you get the growth stage when it's just starting, the cloud is starting to bubble its way upwards through the conditionally unstable environment. It develops into, at this point, it may not be raining very much, and so at this point, it's a towering cumulus. Eventually, the cloud will start to produce rain, and at that point, once it starts to produce rain, it'll actually start to generate a downdraft through the drag and evaporation processes. And once you've got a downdraft associated with your updraft, at that point we say that the thunderstorm has entered the mature stage. So you've got an updraft and a downdraft pair associated with your mature cell. But in a single cell storm, the downdraft is actually eventually going to be the demise of the storm, because you've got this cold pool building up on the ground that spreads, and under conditions of weak wind shear, this cold pool is actually just going to spread along the ground, and eventually it's going to cut off the warm air from the cloud. So the warm air is rising from down near the ground, and as the cold air spreads along the ground, it eventually cuts off that supply of warm air from the cloud, and the cloud dies off. Now, as I mentioned, under certain conditions, you can produce a new cell, but when the types of conditions that single cells form in, that is weak wind shear, it's more likely you're just going to kill off the old cell, and then it dies. Here's a single cell storm in the dissipating stage, sort of what it would look like. It's starting to rain out down here at the bottom, but you can see it's just one big thunderstorm cell in isolation. Okay, the multi-cell storm. Now again, a multi-cell storm is a group of cells that are evolving together, but typically it's a bunch of cells in differing stages of environment or differing stages of development. Each of the individual cells in your multi-cell will go through a similar life cycle to the single cell storm, each one sort of living, on the time scale of roughly an hour. But what will happen is you'll continuously produce new cells to replace the ones that are dying off, and so you end up with a much longer lived system because of that. In terms of conditions in which a multi-cell storm forms, it's a little bit more severe type of thunderstorms and long-lived type thunderstorms, so as you might guess, it forms in environments with more wind shear. So multi-cells tend to form in environments with weak to moderate, we'll say. Weak to moderate wind shear in the environment. So a bit more wind shear than you would typically have for the single cell. This is a photo down here. I think I took this one this spring, just from Lowe's in Bryan, which is a good place to take cloud photos because it's way up on the hill. So looking up to the north, you can see this is a thunderstorm system consisting of several different cells. These are actually in different stages of development. So this guy on the left here is a cell that's just being formed. This guy in the middle is a mature cell. And this guy over here on the right is actually a dissipating cell. So you've got 3 cells here that are in different stages of evolution. And that's typical for multi-cell storms Because the way this works with the multicell storm is that the gust front, under conditions with enough shear, will tend to actually kick off a new cell as it spreads. So notice, you remember that for the single cell, what the spreading gust front did was just, cut off the supply of warm air from the storm, which killed it. But if you have a bit of shear in the environment, then instead of just cutting off the supply of warm air, it'll actually kick off a new cell. And so you have your old cell, here in this case it's a mature cell, but as the gust front spreads, you'll kick off a new cell out in front of it. And this process will continue. So eventually the old cell will start to die off. The one that's being kicked off now will enter the mature stage, and then it'll kick off another new one out in front of it. And so you'll have a progression of cells where they're continually formed on the front edge of the system. The mature cells are sort of in the middle, and then on the back side of the system, you'll have dissipating cells that are dying off. That's kind of how it works with the multi-cell system. Here's just some pictures associated with gust fronts. This guy knocked part of my recording studio down there. Okay, but I'm back set up again. So this guy up here this is a spreading gust front here. You've got I probably should have mentioned this before when I had the picture of the gust front. But the gust front's on the back side of this system. It's the cold air that's spreading along the ground. And often you can identify this by this sort of cloud structure. It's referred to as a shelf cloud. The example I showed before was also a shelf cloud associated with a gust front. And what's going on is that this is the warm air sort of being pushed up and over the cold air as the cold air spreads. And so you end up getting a cloud produced by that as the warm air is pushed up and over. So it's a shelf cloud. This guy down here is also a cloud associated with a gust front. It's actually a cloud that's a little bit behind the gust front. Often behind the gust front, maybe we can go back to that figure real quick. Boom, 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 boom. This guy. So with the gust front, as this guy spreads along the ground and it interacts with the rising air out in front of it, you'll often tend to get the air overturning here and sort of forming a little eddy here because it gets dragged upward by the ascending warm air in a sense. And so you end up getting this sort of eddy out in front of the gust front. And often right in the middle of that eddy, you'll end up forming a little cloud. It's a cloud that if you watch it over time, it'll be slowly rotating around with the flow. And that kind of cloud is referred to as a roll cloud because it's sort of rotating around in place. It's a roll cloud. This was the other shelf cloud I was talking about, the warm air up and over the gust front here. But this guy here was the example of a roll cloud. So often you'll see these guys, they're kind of, they'll sit right in the front of the gust front, and they're just sort of a long, thin cloud that extends over a long region. And if you were to sit there and watch it for long enough, you would see that it's actually sort of rotating in time. And finally, the supercell. The supercell is the most intense of our thunderstorm categories. It consists of a single rotating updraft, but it's a intense rotating updraft, and it's a long-lived rotating updraft. It's actually, these supercells tend to form self-reinforcing structures, so they don't really die off so much as they continue to reinforce themselves. And so because of that, a single supercell storm can actually live for a few hours just on its own as a single cell. Now, as you probably expect, since it's the most severe type of the systems, it's also going to be the type of system that forms with strong wind shear in the environment. So supercells form in environments that have strong wind shear associated with them. Now, as you might expect, because we have a rotating updraft associated with this storm, it's the kind of storm that is most likely to produce intense tornadoes. And we'll talk a little bit about how that works here in the next screencast. Down here, I just got a picture of a supercell updraft. This guy's referred to as a wall cloud. It actually marks the outlines of the updraft. So the warm air that's feeding into the cloud, when it starts to condense, sometimes has a very marked edge to it, and you end up getting this wall cloud thing. And because it's a rotating updraft, this wall cloud will typically rotate in time. You can see lots of examples of this if you Google wall cloud or search for wall cloud on YouTube. You'll get all kinds of examples of rotating wall clouds. And this is the kind of environment associated with this rotating updraft that tends to produce tornadoes. In fact, this example has a little tornado down here in the bottom. This is a figure showing the structure of a supercell storm. I'm not going to dwell on this too much, but what this is on the left is showing a bunch of radar images of the storm at different heights. So we've got 1 kilometer, 4 kilometer height, 7 kilometer height, 10 kilometer height, and then 15. So this was a storm that extended up to 15, 16 kilometers. And the thing I want to point out is the structure down at the bottom. This is sort of something that kind of is the marker, the signature, if you like, of a supercell storm on a radar figure. Often down here near the ground, you get this structure that has a sort of kidney bean shape to it. And it's referred to as a hook echo because you can see it sort of hooks around down here on the bottom. And the place where the updraft is going to be is right here in the hook, sort of this empty space in the hook. What's going on here, you can also see it in cross sections. So these are cross sections. I'll just focus on the bottom one, which is a cross section from C to D through this region. And you can see that the radar signature here of the supercell has this sort of empty space right here. That empty space corresponds to this little hook associated with the figure here looking down from above. And what's going on here is that in a supercell, the updraft is so intense that the air is rising so quickly that there's not a lot of time for precipitation, for rain particles to form. And so as a result, you tend to get the updraft as sort of empty on the radar signature because the radar can't see it. And it's not until you get higher up that you start to produce enough precipitation that the radar will actually see it. This guy has a name. It's called the bounded weak echo region. It's the region here associated with the updraft where you don't see a lot of the actual precipitation because it hasn't formed yet. It can't form that quickly. These are the kind of signatures you look for on radar if you're trying to identify a system as a supercell. Okay, one last figure here. This is showing the three-dimensional structure of a supercell. Often tornadic supercells in particular will end up getting two downdrafts. So you'll have one updraft that's located here in the middle and two downdrafts associated with it, one on this side and one on this side. And the whole system is moving in the direction of the upper level winds, which are shown by the purple arrows here on the top. So it's kind of moving towards the northeast in this example. And so the downdraft that forms over here on this side is typically referred to as the front flank downdraft because it's the downdraft on the front side of the storm. And the downdraft that forms on the other side is the rear flank downdraft. And each one of these guys, each one of these downdrafts will draw cold, dense air associated with it. So they kind of produce their own gust fronts as well. You get a front flank gust front and a rear flank gust front. And typically it's right where these two gust fronts come together. That's where your updraft is going to be. And that's the place where you're most likely to produce your tornado, right where your two gust fronts associated with your system are coming together. Now, I should point out that this arrangement, this structure of the storm is part of the reason why it's so long-lived, because instead of actually killing off the storm, the gust fronts actually sort of feed warm air into your updraft. So it's kind of a different configuration of the gust fronts, and that helps to keep the storm longer lived. Okay, so we'll stop it there for now, and then with the next screencast, we'll come back and talk a little bit about tornadoes.